Hello, Forces Lesson 5, with Lesson 5 already. Centre of mass today. The nice thing about this one is it does not matter at all if you have seen none of the previous lessons. It's like a whole new, wonderful, joyous topic all in itself. Centre of mass, what is it? It's much easier for me to show you rather than talking about it. So get a pen. Hello, Thomas. Hello, Elsa. Shuffle in. You're late. Get a pen or a pencil. You've probably got one near you, haven't you, if you're doing this homework lesson. Try and balance it on your finger. Hey, try and balance it on your finger. Poppy and Siri, are you doing this? If you've balanced the pen, you can use two fingers if you like. If you've balanced it on your finger, then the centre of mass of this pen is there. Just above where your finger is. That's the centre of mass of the pen. The centre of mass of an object, some people say this, you could say the centre of gravity. The centre of mass or the centre of gravity of an object has a lot of different descriptions. We're going to say it's the point around which everything else is balanced. So we looked at moments last week, how much things turn. The moments on this pen are balanced. Heather, do you know the fork? Leveled up. We'll get to the fork. All the moments on this pen are balanced, all right? It's not turning that way. 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 It's balanced, right? Yeah, got it. So let's have a look at a piece of paper. We've got a piece of paper. Let's balance that. So the centre of mass of this piece of paper is about there. I'm going to put a dot. There we go. And so if I'm holding it this way, the centre of mass is there. But if you imagine that this piece of paper is actually like a piece of cardboard or a piece of metal, then even if I was holding it this way around, the centre of mass would still be there. See, it would still balance. Or if I was holding it this way around, well done, Iris, then it would still be balanced, okay? So the centre of mass is like where you can imagine all the mass of the object is concentrated. The object behaves in the same way as if all its mass was there. It's kind of like, on average, where all the mass is in the object. Now, flat symmetrical things, it's dead easy to find the centre of mass of a flat symmetrical thing. If you've got a piece of paper, you can do this with me. Fold the piece of paper so that you get a line of symmetry. It's maths, isn't it? You've done symmetry yet? So if things are symmetrical, they're the same on both sides. So when I fold a piece of paper like this, the piece of paper is the same on this side as it is on this side. So we would say that this is a line of symmetry. Okay? Now we know that the centre of mass of a flat sheet like this is somewhere along this line. But how do we find out exactly where? Karina is good at this. Good. You've got to get another line of symmetry. How do we get another line of symmetry on this piece of paper? Fold it another way. See? Joe is saying I'm very blurry. Am I very blurry to everyone else? Let me know. There you go. Now we've got two lines of symmetry. Paper's the same on that side as that side. Where the lines of symmetry cross, that is your centre of mass. Hey, look, I was pretty close, wasn't I? Look, that was my balancing mark. That's where the centre of mass is on this piece of paper. And it doesn't matter if it's a circle or a triangle. If it's a symmetrical object, then the centre of mass is where the lines of symmetry cross. All right? Now let's level up to forks. Picture's good, okay. So a fork is a little bit different. Although I found out yesterday that this fork is actually annoyingly well balanced. But if I said to you, right, can you just balance this fork on one finger? You probably wouldn't put it right in the middle, would you? Because you have learned, because you live in the world, that if this side of a thing is heavier than this side of a thing, if one end is heavier than the other, you've got to move your finger along a bit to compensate. Oh, good. Oh, hey, nicely sticking around. There you go. So if I actually, like I say, this fork is quite a well-made fork. Look, they've added quite a bit of mass to the other end, the holding end, presumably to balance it out. But that gives you an idea that if one end of a thing is heavier, has more mass, the centre of mass moves along that way. Okay. Hello, Sam. Where is your centre of mass? Where is it? Generally, like around your tummy button. Let's say, yeah, somewhere around your tummy button, let's say. You're happy with that? So a giant could balance you like that way, and your centre of mass would be above the finger, so nice and stable. Or if they put their finger on your tummy button that way, then you would still be balanced. Right, now, put your arms in the air. What has happened to your centre of mass? Has it gone up, or has it gone down, or has it stayed the same? Okay, let's say that when we've got our arms down, centre of mass is around the belly button. Lift your arms up. What's happened to your centre of mass? If someone was going to try and balance you made of stone, like lengthways like that, would their finger go in the same place, or would it have to go in a slightly different place? What do you reckon? Centre of mass higher, lower, or stay the same? There's a 15-second delay on the comments. I hope an answer so that I can put my arms down. I'm getting tired. I'm going to scroll. Come on, you must be giving me more comments than this. No. Up! Yes, Emma! Nice! Up! Well done. Heather, different. Yes, if you raise your arms, you are raising your centre of mass, okay? It's like the same as if you were trying to balance this pen without a lid, you'd probably put your finger there in the middle. But if someone added a bit more to the pen and made it longer, you would intuitively move your finger a bit further along. The centre of mass would be in a different place, right? You've stuck a bit more mass on there, so you move your finger up. It's the same when you lift your hands up. Oh, more mass is now higher, so your centre of mass is raised. Right, let's give you a few questions, okay? See how you get on. Now, yesterday, people were like, oh, these questions, easy peasy lemon squeezy. Obviously, there are some tricks in there. So, those of you who are just getting to grips with the centre of mass, you could aim to answer about 4 of these or more. And if you're like, oh, Laura, I'm all over this, then just check your answers, okay? Because I have been trying to catch you out as usual. Here we go. Janet's back, and I've got a lot of Janet fans. I'm in with Science Alliance. So I've got you, there's 8 things here. There's a spanner, a ball, Janet the dog, a donut, a sort of Libra style balance, a book, a double-decker bus, and a piece of card shaped like that. Can you, if you've got the sheet, you could just put a cross, or if you haven't got the sheet, you could sketch them out roughly and put a cross. Where is the centre of mass of all those objects? And then if you finish that, can you draw a non-symmetrical shape on a piece of paper and cut it out? And have a mull over, how would you find the centre of mass of a bit of paper that wasn't symmetrical? Unless you've Googled it, don't Google it. Then I'll be very impressed if you get that. That's a really tricky one. Mull it over. Okay, well done you lot. If you spotted that the centre of mass in the hammer was in the middle. We did moments, didn't we, turning forces last week, and we looked at how the pivot on a spanner is here. Like if you were turning the hammer like that, the spanner like that, then it would be pivoting around there. So just to confuse you, the centre of mass is in the middle because it's symmetrical. A ball, doesn't matter if it's a 2D flat ball or if it's a sphere, the centre of mass is in the middle. Well done. Janet, well, Janet's got little legs and quite a lot going on up here, so I reckon her centre of mass is going to be somewhere up here. She's got quite a sort of boofy haircut going on, hasn't she? So I'm going to say her centre of mass, like on average her mass is somewhere along this line and maybe a bit more towards her head, like there. The donut, yeah, the donut's a weird one. I'll explain this a bit more after we've gone through this sheet. But yeah, the centre of mass of the donut is actually in the centre of the donut hole. Well done if you said that. Centre of mass of an object doesn't necessarily need to be on the object. The balance kind of depends what's in these little cups here. So if these cups are sponges and the actual balance is made of like solid gold, there's quite a lot of gold down here. So I guess the centre of mass would be quite low. Whereas if these are full of gold and the balance is made of plastic, then maybe the centre of mass would be a little bit higher, but well done if you put about there. Yes, the book, Sadaf noticed that the book, oh, sorry, it's not Sadaf, is it? But there's 2 different ones for the 2 different books. So if the centre of mass is open, if the book is open, then it's fairly symmetrical, isn't it? And the centre of mass would be in the middle there. But the centre of mass on that book would be here, and we know that if a book's shut, that's not going to be the centre of mass, because if you tried to bounce it there, it would tip over. So the centre of mass of the closed book is there. So just like you, when you raised your arms and lowered your arms, your centre of mass moves a lot depending on what you're doing. The centre of mass of a book moves as well. 8 is going to be on the corner. Kim, that is a very good effort, but no, the centre of mass of this one is not on the corner because think about it, then you've got loads of mass on this side and no mass on that side. So that would not balance it. Double-decker bus. We'll look at double-decker buses at the end if you want to do an IGCSE or have a look at a GCSE question. The centre of mass of a double-decker bus is very low down so that it doesn't fall over, but we'll get to that later. All the engine and the complicated bits of the bus are down here, and the top deck is left very empty. That's just for passengers to stop it tipping over. The centre mass of this piece of card. Oh, the inside corner. Sorry, yes. Oh, yes. That would be much more likely, yeah. This piece of card was a good tricksy one, kind of the same as the donut. You've got some mass up here, some mass up here. So on average, the mass of that card is probably about there. That's the centre of mass of the card. And did you draw a non-symmetrical shape on a piece of paper and cut it out? I will talk you through the donut paradox and then we'll do asymmetrical shapes. Yeah, so it's a bit of a weird one, that, isn't it? If you imagine this plastic hoop thing, the centre mass of this plastic hoop is actually through the middle. Imagine, I don't know, if you wanted to hang it from the ceiling, you would tie string all around it, wouldn't you? And you'd have to make sure that the string was kind of gathered in the middle so that it hung straight. You can picture it like that. So centre of mass of an object, not necessarily on the object. And yeah, the other good one to notice is if you've got someone else in the room, ask them to bend over. You can't really see yourself doing it, but if you picture a human bending over, you imagine them doing that, don't you? But that wouldn't work because, you know, more or less half our mass is up here. So if we suddenly moved half our mass like that, if you did the moments turning forces lesson last week, you would see that suddenly if your feet are the pivot, you've got a lot of mass quite far away from the pivot, and you're going to do that. So actually when you bend over, what happens is your bum sticks out that way so that it compensates for your rest of your body going that way. You have a look at that in the mirror after this. Interesting. Okay, have you got a non-symmetrical shape? I'm just going to tear one. I'm going to do a very boring. It's actually I found it really hard to draw a non-symmetrical shape. My brain just wants to go symmetrical. I think I'm going to stick like this. That's rubbish, isn't it? I hope yours is nicer than that. I've just torn some bits out of a piece of paper. How am I going to find the centre of mass of this piece of paper using, I'll give you a clue, if you didn't read Kevin's comment, a needle, something which is traditionally called a plumb line. My plumb line is actually a bit of string with a sort of manky bit of sellotape on the end, but traditionally a plumb line is a bit of string with a mass on the end. So I'm going to use a needle, a plumb line and a pen to find the centre of mass of this. Shall I show you? Maisie, age 10. Listen carefully because this actually, IGCSEs are slightly harder than regular GCSEs. This came up, this was like a 6-mark question at IGCSE. What a gift. What you do is, if your paper is not symmetrical, you could do this afterwards. I'm going to ask you to do this as optional homework. Put your piece of paper onto your needle. Just like stab a pin through the piece of paper and make sure that it hangs loose. Not that loose. Yes, thank you, Kim. It is a cloud, yes. I made a cloud. And then attach a bit of string over the needle as well, so that your bit of string also hangs loose. There we go. And then get a pen. It's just asking for trouble because I haven't got a ruler, but get a pen, mark some lines on, and then complete with a ruler so you've got a line hanging down. Can you see where I'm going with this? Can you see how I'm going to find the centre of mass? What's the next step? There we go. So, we know that the centre of mass of this piece of paper is somewhere down this line, yeah? Because when I hang it loose, gravity pulls the paper down straight to the ground, all right? So its centre of mass is somewhere along here because it's balanced, isn't it? Obviously, if it's not balanced, then it swings back to where it is balanced in this position. So what you do is you stab your needle through in any other place and you just do the same again. And then we're going to get 2 lines across. So yeah, if you want to carry on after this lesson, I didn't ask you to bring the stuff because you're all going to have a different setup. Someone yesterday was hanging like a toy polar bear from a bit of wool. But if you want to use a bit of needle or a bit of badge, this is actually a little broken bit of paper clip that I'm stabbing through the paper here, and a bit of string with something hanging off it, and find the centre of mass of your asymmetrical piece of paper, and then post it on the group to show me, that would be very good. Oh yes, you could use a sharp pencil, exactly. You could even use a match, couldn't you? But that's interesting. Actually, I'm quite glad that I used the same bit of paper. So can you see that now I've hacked a few bits off and made a beautiful cloud? The centre of mass of my paper is in a slightly different place. So there you go. Right, little GCSE question for you now then. Don't worry, it's not really a GCSE question, but oh my goodness, my IGCSEers were so happy when this came up. I've just put all those steps on here for you, on a piece of paper for you. Can you put them in the right order? I won't give you long. If you've got the sheet, then you can just write new numbers on. If you haven't got the sheet, then you could quickly write down what you think is the correct order. So finding the mass, the centre of mass of an irregular object, put these steps in the right order. Just basically tell me what I just did to make sure that you've got it in your head. Of course, the best way to learn this and remember this is to do it yourself. So I thoroughly recommend you do it afterwards, even you, Priyanka, who is 37. Okay, you lot, here's your answer then. There we go. Like I say, best to learn by doing, but if you stick a needle through any part of the card, make sure it hangs loose. That's important, because otherwise it might not be balanced. You need to let gravity pull it down. Hang a plumb line on the end, wait until the card stops moving, mark little dots on the plumb line, and then draw a straight line, and then just repeat. And then where the 2 lines cross over, that is your centre of mass. Right, are you ready to do this cool activity? And I am also going to tell you a physics joke, which went down like a lead balloon yesterday, but I'm still going to tell it, because it's relevant. Right, so that's bits of paper, okay? That's fine. Let's look at the centre of mass of an actual thing, and then, like I say, after that I will, while you're setting it up, because it might take you ages and ages to set this up, it is very frustrating. It is. I'm not going to test you on this. This is never going to come up in an exam. It's a fun activity you can do about centre of mass, but it's also good practice for for getting stuff wrong and not getting really cross. Just flip you so you can appreciate the true joy of my... Oh, is that the right way around? No. There you go. Now you can see Jurassic Park mug in all its glory. So, what you need for this activity is a lot of patience, a lot of resilience. You've got to be able to handle watching people going, yeah, I've done it, and you still haven't done it, and not get cross. Get a spoon and a fork and attach the spoon and the fork together. So put 2 prongs of the fork on the outside of the tip of the spoon and 2 prongs of the fork on the inside of the tip of the spoon, like that. Like that, see? It's already annoying and difficult, isn't it? But you can always just watch mine. See? So I've got 2 prongs on the inside of the spoon tip and 2 prongs on the outside of the spoon tip, and they are attached together to make a sort of little contraption like this, a kind of seesaw out of cutlery. Okay? Emma doesn't have patience. Wow. You do need some really for physics, don't you? But if you're going to get good at physics, there's a lot of, happens to me all the time, there's a lot of, I don't get it, I need to read another thing, I don't get it, I need to read another thing. Oh, I get it. When you've done that, don't worry, I'm going to give you loads of time after this. I'm going to tell you why centre of mass is important. Isaac, I'm making your teeth feel funny. You'll see that you've got 3 holes now, haven't you? In the middle of this contraption. You've got a top hole, a middle hole, and a bottom hole. Thread your fork through the top hole, like that, okay? So I kept saying fork yesterday. Thread your match through the top hole, like that. All right. Thank you, AU, keeping the faith. And then balance. Don't worry, I'm going to give you loads of time. I'm just going to do it so that people can see what it looks like. And then balance it on the edge of the mug. This is the bit that is extremely tricky. you got to practice. You could like move the match so that it's at a different angle. Sometimes you get it balanced, but actually the cutlery is still touching the table. I'm going to have to lift that up a little bit. Okay, here we go. People have got too good quality cutlery. Sorry. Mine needs to go up a bit more actually. Well, it's hanging off the table. I guess that's okay. There we go. Let me show you that. Gareth, if you don't have matches, try it after with, you could get a cocktail stick or maybe like a little twig. There you go. See that? Like that. Oh, blooming flip screens. There we go. Okay, so while you're trying to get that sorted, I'm going to tell you why centre of mass is important. Because, to be honest, I've taught centre of mass for quite a few years and I never looked at this before. And when I did a bit more research, because I do for you, because you asked me the brilliant questions. Ah, good, well done, Heather. Sadaf, I did this a long time ago as part of the gravity show, I think. Yeah, why is centre of mass important? Well, we have done thrust, haven't we? We've looked at how rockets go forward, right? So a rocket travelling in space, where there's very few air particles, if it wants to go forward, then it fires up its engine, doesn't it? It basically makes an explosion happen inside it, and therefore the rocket goes forward. That explosion has got to act on the centre of mass of the rocket to make the rocket go forward. Imagine poking a rocket so that it goes forward in space, and now imagine accidentally poking it at a slight angle. What would happen? Oh, cotton buds! Gareth, great idea. If you haven't got a match, go and get some cotton buds. The rocket would start spinning. If that explosion in the engine happens at a slight angle, the rocket is going to start spinning, and obviously it's very difficult. It uses a lot of energy to slow rockets down in space. So that's one reason that centre of mass is really important. Another way that centre of mass is really important, if you've ever seen rotating machinery. You okay? You got that? Yeah. Yeah, if you've ever seen a bit of machinery that's rotating really, really fast, obviously the centre of rotation has got to be the centre of mass of the thing. Imagine like a cog, but its centre of mass is on one side. If it spins really, really fast, it's going to become very unstable very quickly. Another reason centre of mass is important is, the joke is coming, it's imminent, is that centre of mass allows you to really simplify equations in mechanics. So, picture a hammer, if you will. This is such a ridiculous, like, mechanic style question. A hammer is flying through the air. Why? I don't know. But if you imagine the motion of a hammer that is being thrown through the air, it's quite complicated, isn't it? Like, it's spinning around. But the cool thing is that the centre of mass of the hammer acts as if you've just thrown a ball. Well done, Joe. So, say the centre of mass of the hammer is there. The hammer would spin around the centre of mass, okay? But the centre of mass of the hammer would behave just as if you'd thrown a simple ball. And they use that kind of calculation for like if a plane has an accident, like say a plane crashes. The movement of the plane, obviously very complicated, so what they do is they look at what the centre of mass of the plane did, and that can tell them a lot about, like, say, what caused the explosion, why the plane fell out of the sky. Which leads me to my physics joke. And then, hiya Jack, and then we'll light the match. Please, if there's no adults in the room, do not light the match. I'm going to light the match in a minute. You can watch me and then you can tell your adults, and I'm sure they will do it because this is super fun. If there's an adult in the room, then wait a second and we'll do it. But I'm going to tell you this joke because it's a good, very traditional, old physics joke, which explains why centre of mass is important. Right, a gambler wants to bet on a horse race, but they know that gambling is a total mug's game. So they want to be absolutely sure that they're going to pick the right horse, that they're going to choose the horse that's going to win. So they go to a biologist and they say, you have to tell me which horse is going to win. The biologist goes away, works for a week, looks at like all the genetics of all the different horses, all the horses' family trees, and comes back and says, no, I can't do it. It's just, no, there's not enough information in this. There's no way I'm going to be able to tell you for sure which horse wins. So the gambler goes to a mathematician, a statistician, and the statistician looks at which horses have won, which races before, gathers all the data about the top speeds of each horse, puts them all into a computer model, comes back after a week and says, no, I just can't do it. There's too many variables. Like, I've got it down to sort of 4 horses, but there's no way I can tell you for sure. The gambler goes to a physicist, and the physicist comes back within a day and says, yeah, absolutely sorted. Got it for you. Horse number 4 is going to win the race. The gambler says, what? That's amazing. Like, how did you work that out? No one else could do it. The physicist said, super easy. First of all, imagine all the horses are spherical balls moving in a vacuum. Yeah, because physicists are always making like wild assumptions and doing calculations that simplify things to the point where they don't relate to everyday life. So if all the horses were balls, because their centre of masses would be in the middle, then horse number 4 would win. But the horses aren't balls. The physicist hasn't realised that lots of other things going on in real life that mean that they don't know which horse is going to... All right, let's look at this then. Let's assume you've all finished. Right, here we go. Where is then, please, the centre of mass? You can't tell me exactly. We had a chat about this yesterday. But where is the centre of mass of this construction here? Where's the centre of mass of the fork and the spoon? What do you reckon? Thank you, Emily. Yeah, there's just a huge delay. People are now like roaring with laughter. Where's the centre of mass of this? If you haven't done it, don't worry, use mine. Where's the centre of mass of the fork and the spoon together? Okay, what do you reckon? This totally flummoxes year 11s. Well, let's light the match. Once again, cannot overstate this enough. If you haven't got an adult with you, do not light the match. Nathaniel, too embarrassed to admit that he thought that was hilarious. Right. Oh, Esther is saying edge of the cup. Nice. Right, lighting a match and holding a phone. Oh, I need to flip whilst holding a light match. Right, this is why you have adults with you. What about? Is this going to help you work it out? Oh, I love this activity. So if you're in my year 10 or 11 class, you come in and this is set up and you're like, what? That's a crazy balancing trick. And then we light the match and everyone's like, seriously? Elliot, what are you telling me? Elliot says, nice use of pivot point, Elliot. 10 stars. Where the pivot point is, where the match touches the mug. Absolutely fantastic. Well done. Yeah, I hadn't thought about that. But this is the pivot point. And the fork and the spoon are balanced around the pivot point. Very well done. Look at that. Isn't that great? There you go. So try that at home if you haven't already and get an adult to light the cup. So yeah, actually, yesterday I said that the centre of mass was here, of this spoon and fork, was here. And then a couple of very smart, thoughtful adults said, well, actually, it could be really anywhere. It could be anywhere down here. So the centre of mass really could be quite a little bit further than the match. Because in a way, if you think about it, we've only found one line of symmetry. Does that make sense? Again, you know, no one's getting tested on this, but for the people who really care about this stuff, we've obviously balanced the match over the centre of mass of the fork and the spoon. But yeah, it could be like there or there or there. It could be hanging in the air around here. Okay, right you lot. Very well done. That is, strictly speaking, the end of our centre of mass lesson. Except, I know that a lot of you home edders do IGCSE, because there's fewer practicals and it's all exam. So I have got an IGCSE question for you, as ever, and I'm also going to tell you, not teach you because I don't expect you to remember it, but I'll just tell you like a few cool keywords that you'll come across if you do GCSE. And introduce you to a few more concepts. But for the rest of you, some of you are like 5 and 6. Well done. That was a fantastic lesson. If you want to find the centre of mass of your irregularly shaped piece of paper using a bit of string and a toy or whatever and then post it on the group, that would be really nice. I would love to see that. Otherwise, have a fantastic day. So if you're new and you like that and you want to carry on and you want to help me out, you could like my Facebook page. That would be amazing. I'm getting like tragic amounts of fulfillment from people liking my Facebook page. That's great. If you really liked it and you want to support me, then I am still only doing this. I can only justify the childcare because some people are supporting me monetarily. If you click sign up on my Facebook page, like the homepage near the like button, then if you go to sign up adults, it takes you to this website called Patreon, where you can support me with £3 or £5 or £10 a month. And in exchange, you get various thank yous, like anyone who's supporting me with £3 a month is going to get rainbow glasses, and anyone who's supporting me with £5 a month or more is going to get the magazine, which has arrived. It's here. And like a fool who's never used social media before, I don't have it with me, but it's on Snow. It's got like a little double page spread, like a comic to show Shackleton's adventures, and it's got the science of do Yetis exist, and it's got a teeny tiny little craft that you can cut out, and I'm very proud of it. All right, end of ad. Go to Patreon and sign up if you are in this and you're really enjoying everything I do, or just come for a chat about plastics and see how you go, or like my Facebook page, thank you. Okay, let's do some IGCSE. Right, got to show you my toy bus. Come with me. Got to show you my horribly messy office. Right, here we go. A London bus. Let's learn one new phrase, okay, and talk about why things don't fall over. Thanks, Nathaniel and Julia. Thanks, Sadaf. Let's say the centre of mass of a London bus is right at the top, okay? They've made the top heavy and the bottom is not as heavy. So on average, bicep, the centre of mass is here. If that bus, for reasons, which let's not go into, starts to tip over, say, let's look at what happens. If the bus starts to tip, the bus is now pivoting. People who came last week, where is the pivot of this bus? On what is it pivoting? Laura, not quite in the middle. I'm going to tell you why the centre of mass of a bus is not usually in the middle. The pivot point is the wheels. Yeah, you got that? So we've got now a moment. We've got the bus wants to turn this way, and the bus could also turn this way, all right? If the bus sort of tips a bit like that, the centre of mass is still acting within the base. So the new thing that I want to teach you, last thing, is this word line of action. The line of action is the invisible line from the centre of mass to the ground. So you can imagine it's like where gravity is pulling the centre of mass. So obviously when the bus is straight, the line of action just goes from the centre of mass all the way down to the ground. Nice, the bus is balanced. If the bus starts to tip, then the line of action is like here, see? So if the bus tips and the line of action is within the wheels, that's fine. The bus will still just fall flat again. If the bus tips and the line of action is over the pivot, then you've got some sort of crazy like action film scenario where the bus is just balanced. But if the bus tips to the point where the line of action is beyond the wheel base, okay, so this is what we call the base, the space between the wheels. If the line of action goes straight down and it's not over the base anymore, that's when the bus will fall over. So now let's move the centre of mass right down here to near where the engine is and see what a difference it makes. Now let's try. So the bus tips, the bus tips, the bus tips. Can you see how much more the bus has got to tip? That's crazy, isn't it? You would think, looking at that if I let go, the bus is definitely going to fall that way. But actually, if the centre of mass is really low and the base is nice and wide, if the centre of mass is low, then look, the line of action is still over the base. So it would still trip. It would have to get like all the way like that before it fell over. And this is why this is true. London buses have very wide bases for a start. They make the wheels nice and far apart. And they also put try and make the centre of mass as low as possible. So there's only seats at the top, and all the engine and all the complicated stuff is down here. Here we go. Usually the IGCSE question relates a bit more to what we're doing, but actually centre of mass doesn't really come up until you're a bit older. Flip. There we go. Okay, so this is 2 marks. I think this is really important, this. I don't expect you to get this right, but I think if every week you're looking at a GCSE level question and you're working out the little tricks and schemes, you're going to get really good at this. Thanks, Laura. Thanks, Jono. An event involved paddling a homemade raft down a fast-flowing river. The rafts were made using empty barrels. Below are the designs of 2 rafts. Okay, design A has just put all the barrels in a row. Design B has stacked the barrels on top of each other into a little pyramid. Compare the stability of the 2 raft designs. Give reasons for your answer. And that's 2 marks. So the most important word in this question is this one. Compare. So if I was asked to compare the height of me with the height of my daughter, I would not say I am tall. I would have to say I am taller. That's comparing, okay? A lot of people lost a lot of marks for talking about a raft, but not comparing. Use comparative language, please. Hi, Karis. Good to see you. Thanks, Rebecca. Thanks, Heather. It would be nice if we tidied up ever. Design A is the best. Rebecca, that is correct. Do you want to know something really annoying? The first sentence on the mark sheet is raft A is more stable. No mark for identifying the correct raft. No mark. Only marks for the explanation. Raft A is more stable. I mean, at this level, you're not doing your IGCSEs, are you, this year? So well done if you got that Raft A is more stable. I think you should give yourselves an extra mark for that. Raft A has the lowest centre of mass. Look, it's got to be compared, okay? And because Raft A has the widest base, or is the widest, all right? Oh, well, there you look. You could have said the barrels are spread out the most. So you don't need to use, like, the absolute scientific language, you just need to have the correct idea. So the barrels are spread out the most. Saying the barrels are spread out wouldn't work because that's not comparing, all right? Or you could say the opposite. You could say that raft B is less stable because it has a higher centre of mass and the narrowest base, all right? So the takeaway from this is, show me again. Oh, Heather, well done, got a mark. Very good. Yeah, the takeaway from this is that for things to be stable, they have to have a wide base and they have to have a low centre of mass. That's why I'm always kicking the high chairs in my house, because high chairs have to be very stable, so their legs are a ridiculous angle, so their bases are massive, so that if a child, I don't know, decides to like do this, then they can't possibly knock it over. Whew. Right, that is the end of this lesson on centre of mass. Thank you ever so much for coming. Joe got no marks. Well, you make that sound like a negative thing, Joe, but you have been in a physics lesson by choice for 45 minutes and continued to listen to everything that I've said and all my explanations. So give yourself 10 marks for resilience. Resilience is so much more important. It doesn't matter if you don't understand it now, you'll understand it in a year or 2 years or 3 years or 10 years. But if you've got the kind of brain now that is going, I don't get it, I can't do it, I don't get it, that is so much harder to learn how to reprogram your brain to think like in a more positive way and kind of relax and ask questions and put the effort into working it out. Oh, I mean, if someone just doesn't get it and it takes me like 20 explanations, that is fine. But if someone's going, can't do this, don't get it, too hard, angry face, it's really, really difficult to get into people's brains like that. Really difficult to change people's attitudes. Is it possible to make A topple? Yeah, good question. Could you topple this raft over? Yeah, definitely. So it would have to, I suppose, pivot in the water, wouldn't it? So it was like that. Then it would, I don't know, in some sort of weird Tom Cruise film, it would be balanced on the water. But obviously, as soon as the centre of mass became